Welcome. In this lecture, we are going to talk about stability comparison of fixed and variable frequency digital current mode control with some experimental case studies. So, here we are going to talk about, we want to revisit the mixed signal fixed and variable frequency current mode control method. Then we want to show experimental results of stability status with closed current loop, and we want to show some assessment. We want to make a comparative assessment of fixed and variable frequency control method, current mode control method. So, we already have discussed about mixed signal peak current mode control. So, we are not going to spend time on it, and we know the is functional waveform, and we also know the mixed signal constant off time peak current mode control. Only difference between the fixed frequency peak current mode and this peak of constant off time peak current mode. Here the off time is fixed and in fixed frequency time period is fixed, but both actually have the peak current based architecture. In case of constant on time current mode control, it is a valley current mode control, where on time is fixed and it is the valley current mode control, and we are not going to show valley current mode fixed frequency control. This is not so popular, but this constant on time current mode control is very popular, because if you are talking about data center application, even for low duty ratio POL application, where the on time is small, and for that on time peak current mode fixed frequency will be stable, but it will be difficult to implement when you go for high frequency, because you have to take care about the comparator action and everything. But this constant on time is very popular for low duty ratio operation, because the on time it is just the timer, and during off time you will get a large time. So, I am talking about the scenario when the duty ratio is very large and you will get like this. So, in such cases, this constant on time is a very popular architecture, where this is your reference current. So, this is particularly for low duty ratio high frequency DC-DC converter. Okay. And we have shown in the earlier lecture that this valley current mode constant on time and peak current mode constant on time, both are inherently current loop stable irrespective of the duty ratio. Whatever is the duty ratio, the current loop is stable. So, now we have discussed the FPGA implementation aspect of variable frequency current mode control, like a constant off time peak current mode control, as well as constant on time valley current mode control, and we have also discussed the fixed frequency peak current mode control in detail in lecture number 75, 76. So, we want to show the experimental case study. So, at 2.5 volt input for peak current based architecture, which is the case of peak current mode control, here with RAM we are talking about, and here we are considering 2 ampere for the valley current mode control. That means, for constant of time. So, these two are peak current mode control, and we have considered 3.4 ampere is the IREF. So, for both these cases, for this case as well as this case, but for constant on time control, we have considered the IREF to be 2 ampere, because this is a valley current mode control, and at 2.5 volt input we have selected the on time and off time in such a way. So, T on is found to be 2.4 microsecond and T off is found to be 2.6 microsecond. So, they are very close to 50% duty ratio, because our effective time period we want to be 5 microsecond. Okay. So, this switching period is 5 microsecond, because we are using fixed frequency control. Okay. Now, when you decrease the input voltage from 2.5 to 2.25, so we have selected T on T off for this case, where the input voltage, that means these all are designed for V in equal to 2.5 volt, but and these are all closed current loop, we have not closed the outer loop. Now, what will happen if suddenly decrease the input voltage? So, naturally for this case, for constant of time, the time period, that means we have FSW which is 200 kilohertz. Here FSW 1 we know it will be smaller than FSW, and here FSW 2 will be smaller than FSW, and here peak currents are fixed, here valley current is fixed, but these two are perfectly stable, and here it is stable by using ramp compensation, otherwise it was unstable, we saw in lecture number 93. Now, if we reduce that input voltage to 2 volt, then FSW is still 200 kilohertz, but you will have a subharmonic instability even with ramp compensation, because we have not considered large ramp, we have just considered a ramp which is not enough to fully stabilize the current loop. So, we need to increase the ramp, and we have discussed this ramp and you can see this current reference for each cases, they are not exactly identical. Why? Because if you consider this is without ramp, now with ramp we will have something like this. Now, you have a current loop instability problem here. Here let us say here. So, since these 2 points are different, that is why the subsequent points, one is higher, one is lower, because it is because of the ramp, and ramp if your hitting point, that means its timing is different, then naturally these values will be different, and as a result the effective peak of the inductor currents are different. Even though you set a reference current, this is because of using this ramp. So, the actual inductor current will not be fixed, because the ramp will change it, and if the subharmonic is there, ramp will be different. And this is one of the problem of ramp compensation, because if you want to precisely control the current reference or peak current even for a high duty ratio operation, then if you add ramp, then this precise current control of the peak current is not possible, because ramp will actually set the revised current reference or updated current reference, which is smaller than the actual peak current reference current, and that is why. But if you consider constant of time, they are fixed, and if you consider constant on time, the valley current is fixed. But the drawback here, FSW1 is smaller than FSW, and FSW2 is much larger than FSW, but they are all stable for these 2 cases, stable without any ramp. So, in summary, fixed frequency control we have frequency fixed, but in constant on time current mode control we saw that frequency was increasing with decreasing input voltage, and this is exactly what. So, switching frequency is inversely proportional to V in. So, mathematically we have discussed. Here if you see the switching frequency, it is not directly proportional, but if you take an incremental factor, that means if you take, what do you say, you have V in, that means if you take this guy, that means if you say 1 minus V 0 by V in, I would say V in minus V 0 by V in. So, this is the term, and we want to relate how this input voltage is related. So, what you will get? You will get, that means I can take V 0 out. So, if you take, so if you 1 minus V 0 by V in, and that means if you see switching frequency is proportional to this factor, that means if V in is decreasing, this guy will increase and this effectively decrease. So, switching frequency decrease. So, the switching frequency, so it will be highest at the highest input voltage, but at the lowest input voltage it will be lowest. So, here it will be highest at the lowest input voltage, but all this problem can be overcome if we can adapt. You can make adaptive on or off time based on whether it is a constant on time control or off time control, and in digital platform it is very easy. Even we do not need a whole lot of digital control for the outer voltage to inner current, they can be purely analog, but your timing signal will be digital domain, where you can play with this adaptation in timing parameter, so that you can maintain the switching frequency. So, in summary, we have discussed various both mixed signal, fixed frequency and variable frequency control we have revisited. We have shown some experimental result regarding their stability status. For fixed frequency we have considered ramp compensation, and we saw that the RAM compensation was not enough, when you further increase the duty ratio, then you need to increase RAM compensation, and that may slowly take the current mode control slowly become voltage mode control by adding more and more RAM. But we saw that in case of constant on time or off time, there is no problem with the current loop stability, and we also saw some comparative assessment, but they have a problem in terms of frequency variation, which can be anticipated by the means of timing adaptation. So, that means we have shown some comparative assessment between fixed frequency and variable frequency current mode control. That is it for today. Thank you very much.